Hey, welcome back. Last time we were talking about lines, and now we're going to talk about planes. We're going to come up with what the equation of a plane is, but it's not a vector function. So remember, vector functions either look like lines or curves in space. They really have only one dimension of movement. So a plane isn't going to have that same structure. But our discussion of what we're talking about really does fit in with lines because lines and planes interact in a certain way, and we're going to see that writing an equation for what a plane looks like fits in with all the other vector things we've been talking about. So that's why it's here, even though it's not a vector function. All right, so the question that's going to motivate us here is, does a plane have a direction? Okay, so there's a plane. Here we have a plane. Doesn't have a direction. Well, I mean, if you walk in the plane in multiple ways, there's a lot of different directions you can walk in a plane. Um, but what's special about all of these directions is that the plane, all of these directions are perpendicular to one additional vector. So well, no matter what the plane is, if we were to rotate, if the plane looks like this, here's a plane, and we've got these points, and we're on this plane. Well, there's always one vector that's perpendicular to the plane. All right, and so just like a line has a direction, a plane has an associated vector to it. So let's write down these things. So there's one vector that is perpendicular to the plane. It's called the normal vector. So normal is another word for perpendicular here. So we're going to be talking about the normal vector to a plane, and that's that vector that is perpendicular to the plane. All right, so you should recognize that if I give you a normal vector, well, this plane is perpendicular to the normal vector, but so is this plane, so is this plane. All of these planes have the same normal vector. So just like with a line, a direction doesn't define the line. You need a line, you need a direction, and a point. So for a plane, you need a point and a vector, the normal vector, and that will completely define your plane. All right, so how do we set this up? Let's look at our plane. Hello plane, and then here's our vector 0, or our origin 0, and let's look at any point. So this is our point R on the plane. And then let this be our special point. This is R naught. R2, R naught. So R naught here is the point that we know is on the plane. So let's look at R minus R naught. Right, if we take R0 plus that, we get R. So R minus that, we get R naught. Well, this vector, R minus R naught, this vector, maybe we'll choose a different color here, this R minus R naught is going to be perpendicular to our normal vector, no matter where you are on the plane. This is perpendicular, or if R is over here, then this vector, R minus R naught, is perpendicular to our normal vector. So if we're writing down an equation for what it means to be a point on the plane, this point on the plane, all points on the plane satisfy that r minus r naught is perpendicular to n. And we know how in vectors to write down an equation when something is perpendicular to another thing. Right? So that means that our equation for our point for any point on the plane satisfies normal vector dotted with r minus r naught is equal to 0. What does that look like? So the normal vector, so we're going to use ABC again. So this is a little bit confusing because before we were using ABC to be the direction of the line. Now we're going to use ABC to be the direction of the normal vector. So depending on whether you're dealing with a line or with a plane, ABC means different things. But if we had ABC dotted with x minus x naught, y minus y naught, z minus z naught, so this is our r minus r naught, we have ABC dotted with that is equal to 0. So this is the exact same equation, just written out with the equation for what n is, and written out for what r is and what r naught is. If we expand that, right, if we actually apply the dot product, if we evaluate that dot product, what do we get? We get a times x minus x naught plus b times y minus y naught plus c times z minus z naught is equal to 0. This is another good form for a plane. This should look very similar to the point slope equation for a line, right? And then if we were to expand this, right, if we expanded this, what do we get? We get ax minus ax naught. We get by plus minus by naught, and we get cz minus cz naught. If we take all of these constant terms, right, these are just numbers. They're numbers because x naught is a number, y naught is a number, z naught a number, and abc are numbers. And we bring those all to the other side, and we let d be equal to ax naught plus by naught plus cz naught. Then this is the last equation of a plane. Also an equation of a plane. All right, so again, recognize that this is not a parametric equation of a vector function. This is a completely different type of equation. Right? We've actually, what this is saying is, anytime you have an equation, you have an equation in 3D that looks like x equals, looks like sum ax plus by plus cz is equal to d. That is the equation of a plane. So, for instance, when we see something that looks like x equals 2, x equals 2, normally what we think about when we think about x equals 2, we think that's the equation of a line. But when we live in 3D, x equals 2 is the equation of a plane where that looks like 2 comma y comma z for any y and z. Another thing to say, okay, so this is x equals 2, so it's of this form, ax plus by plus cz equals d, where a is equal to 1, b is equal to 0, c is equal to 0. So the normal vector is 1, 0, 0. So 1, 0, 0, if we would draw in a picture, if we have our x, y, z, let me draw a better line there. If we have x, y, z, then x equals 2 has as its normal vector just a vector that's in the direction um, of the positive x-axis. And so it's this plane that goes through x equals x, that like 2, 0, 0, but that is parallel to the YZ plane. All right, so here, so what we've applied here is this key idea that you can read the normal vector off of coefficients of the x, y, and z in this equation. All right, so let's stop here for now. The next video is going to be applying these ideas about planes and working them at the same time with equations of lines. They interact in a number of different ways that get to dot products, cross products, etc. All right, see you soon.